All right, so yesterday we started talking about forces and we talked about forces and resultants and free body diagrams, what a force does, right? So it can change the direction of motion or the
Um,
speed. Yes?
just to confirm, we were done with Newton's second law as well, right?
No. We've done the
Okay.
first law. We'll be doing the second law today.
Okay.
Uh, right, so a force can change direction or change the velocity, right, or the shape of a body depending on how it's acting and what kind of body it's acting on. Then we talked about Newton's first law, which is an object staying at rest or moving in a continuous straight line at constant speed unless acted on by resultant force, which is also an unbalanced force. And a resultant force may change the velocity of an object by changing its direction of motion or its speed. Then we talked about resistive forces, right? Friction and air resistance. Friction is the broader category, right? Air resistance is a type of friction. And so, right, objects moving through the air or moving through liquids will experience resistance in that fluid, as I mentioned, right? Fluid in terms of physics is anything that flows, right? So that includes liquids, that also includes gases. So, we talked about friction. We talked about the right magnitude of force required to move an object when there are resistive forces acting on it, and the lesser the resistive force, the lesser the force you need to apply and energy you need to use to get an object moving. Then we talk about mass inertia, right? So inertia is the opposition of that a body experiences to its changing its state of motion, right? So if it's moving and it suddenly comes to rest, then right it responds by lunging or lurching or just falling in the direction of in which it was moving when it stopped. And if it is at rest and you suddenly make it move, then it will you know resist it by going in the opposite direction of the movement because it wanted to stay at rest. Right now, this happens more when the mass of the body is greater, so there's more inertia in it, and also right more if it's sudden. So right, if for example a car is braking lightly over a certain distance, you won't feel it as much. It's not like it's not there, you just won't feel it as much, right? Because it's not you know happening all at the same time, right? If it's more sudden, if there's like an emergency brake stop, right, then it's more apparent. Okay, now today we will talk about Newton's second law, but before doing that, we will cover a practical, right? And this practical is given in both the IGCSE and the O level textbooks, and it is to experiment on the effect of force and mass on acceleration. Let's put that up there. All right, so the practicals in your textbooks are given in those red boxes. The setup of the experiment is pretty simple. You take a trolley. So that's an apparatus, right? Not the kind of trolley that you have at the supermarket. All right, so it's a small apparatus with wheels. At one end, you attach a ticker tape timer. Now, what this device is it's a paper ribbon and it's going through sort of like a device that puts a dot on it at regular time intervals. Now, what those time intervals are can be set, or it depends on the type you're using. So at regular time intervals, right, it's going to put a dot on the paper ribbon that's passing through the device. You need a slope, and you need to set up a slope, and you also need some elastic bands. And some mass, additional mass. And so this experiment is going to work in like two different ways. The first is where we are experimenting on the effect of force, right? And the relationship between force and acceleration. And in this case, we're going to keep the mass constant. Now, in experiments, they're always right. So the variable that you want to test, basically what you're testing over is the effect of force on acceleration. So in scientific terms, this is called the independent variable. Why is it independent? Because it is under your control. You're the one that is changing. Acceleration is a dependent variable. Why? Because you will be noting in this experiment how the acceleration is affected by changing the force. So that's a dependent variable. So this is what you're studying, right? What you are studying. And then, right, the mass is the constant, right? Because we will learn that mass also has an effect on acceleration. But if there are more than one independent variables, and so it will become difficult to actually reach a conclusion based on the results you get, because you won't know, oh well, right, did this happen because I changed the force, or did I change the mass, or what's going on? And so you keep as many things constant as possible. And you basically study one thing at a time. Okay. So what we're going to do, and let's see how well I'm able to do this. Probably not too good. Right. So you have like a not that much, but right. Come on. Okay, you got a trolley on a slope. Right, you have your device here, right? This could be a ticker tape, or it could also be a motion sensing device, right? If you want to go electronic. And right, the ticker tape is attached to the trolley. I've drawn something over here. Wheels. And on this end, let's change the color to make it clearer. You have attached elastic band or elastic string. And what you're going to do is, after you set it up, you will pull on the elastic string, right? And you will make the trolley go down, and you will, right, practice so that, right, the force that you're applying is the same. So right? You're applying the same force on the elastic. And how will you figure that out? By how much it's stretching, right? So you're trying to stretch it to a certain length, and that stretch, right, is equal to the force you're applying. And this is something we'll get into today, which will talk about extension, right? So force and extension. So, right, you keep the force you're applying on it the same for the length of the slope. And as trolley moves, right, at a regular time interval, for example, every second, the ticker tape is putting a dot on the tape. And what you'll notice is that, right, as the trolley moves, because you're applying a force on the trolley throughout, the dots on the ticker tape, right, first they're close together and then they start spreading out. Right, so the distance between them starts increasing. And what this is showing, so if it's a 1 second interval between each dot, and so the distance between them is basically telling you that, oh, it's getting faster for every second it's moving, right? And so if the speed, right, so speed is distance over time, we know that, or velocity. We know the time is 1 second. You can measure the distance and you can get the speed. And what we'll notice is that the speed is actually increasing, right? Or in this case, velocity. And that is increasing per unit time. That means that the trolley is accelerating. So when a force is applied on an object, changes its velocity, that means acceleration is happening. Now, right, this is the first step. Now you want to check, well, if I apply more force, will that have an effect on the acceleration? And so you repeat the experiment. With, for example, 2 or 3 elastic bands attached at the same time.
Just
Yes,
a question. What is a ticker time that he just said?
it's a device that, as I mentioned, right, there's a paper ribbon attached to it, and it puts a dot on that paper after a regular time interval, right? So you can either set the time interval, right? It could be 1 second, it could be 5 seconds, depending on the kind of experiment you're doing. So when you turn it on and you're moving the paper through it, after every second or 2 seconds or 5 seconds or whatever the time interval is set, it will put a dot, a mark on that paper,
Yeah.
right?
Okay.
And so as you are moving the paper through that ticker tape device, right, the ticker tape timer, as I mentioned over here, the time difference between each dot is the same, right? So these dots that are close together, right, are all after 1 second. The dots are getting further apart, they're still after 1 second. So the distance between the dots is increasing. That means the paper is moving through the timer more quickly each second.
Okay.
Do you understand?
Yes.
Right? And so we can use that because we know the time interval is 1 second. In this case, we can measure the distance between two dots, and then we can take the speed, right, at which the trolley is moving. Why are we getting the speed of the trolley? Because we're pulling the trolley, the paper ribbon is attached to the trolley, so the paper ribbon is moving at the same speed that the trolley is.
Yeah.
Okay?
So will the speed show on that paper ribbon? The dots, right?
Yeah. I mean,
Okay.
we'll calculate the speed by measuring the distance between two dots on the paper.
Okay.
And we'll notice that the speed is changing. It is increasing as it's going down the slope, right, for the whatever force we are applying. And so that will
Okay.
show us that, right, it's actually accelerating.
Yeah.
Right?
Okay.
The reason we put a slope is to actually make it easier for the trolley to move.
Okay.
Now, right, once you've done that with one elastic band, you're going to repeat it with 2 or 3 elastic bands. And right, if you've ever played with elastic bands, you know, the more elastic bands there are, the more force is required to pull on them, right? That's
Yes.
right. So more force is required to pull on them. And so you do everything exactly the same. The only difference is that the number of elastic bands is more. And so if you are pulling them, so draw it over here, right? So you've got another elastic band and you're pulling it for the same extension. But because the two of them together, you need to apply more force, right? And when you're applying more force, you know that a force is a push or a pull. In this case, it's a pull, and that force is being experienced by the trolley. Again, the trolley will move down. Repeat the experiment, the distance between the dots on the ticker tape. And what you notice is that this time the dots are even more spaced out, right? So you start off again, right, with less, and very quickly the dots, the space between the dots is greater as compared to the first experiment. And so this tells you, right, that the speed is changing even more quickly.
So it means that the speed of the trolley is getting faster.
Hmm?
Like the distance between those dots, it is changing very quickly, right? So does that mean
Yes,
that the speed of the trolley is getting faster, right?
yes, and it is changing, which means it has more acceleration
Okay.
as compared to the previous one. And from this, we can conclude, right, that the more the force is applied, the greater the acceleration. That is a conclusion that we can reach.
Okay.
Now, that's one setup for the experiment. The second setup is measuring the effect of mass, relationship between mass and acceleration. And in this case, as I mentioned, you keep other things constant. So mass will be the independent variable in this case. Acceleration will be the dependent variable. So you will be changing mass, you'll be noting its effects on acceleration, and you will keep the force constant. That means, right, the force constant means you will only use one elastic band. Right, what you will do is use different masses. So the setup is the same. The difference is that, right, except because you're changing masses, right? So one elastic band and you will pull it to a certain extension, and that will be equal to, right, that will show how much force you're applying on it, right, equal to the force you're applying on it. But what you're doing is that you are increasing the mass, right? So you can either place a known mass on top of the trolley, or you can stack two trolleys on top of each other. Whatever the case is, the mass is increasing as compared to the first setup with one elastic band. And what you notice is when you're pulling it down the slope, the distance between the dots on the ticker tape, and I might not be as accurate with my dot placement, but what you notice is that the dots are not as far apart, right, as they were in the first experiment. Right, so you can see that the distance was growing. The distance is growing, again, this is probably not as accurate, but the distance is growing, but it's lesser comparatively. So there is, right, the trolley is going faster, right, as you're applying force, but the amount by which, the gap or the distance between the dots is, right, lesser comparatively is lesser comparatively to when there was only just the trolley. Right? And so what we can conclude from this, if I'm able to squeeze it in over here, is that, right, so again, we take the distance, we know the time, we measure the speed is changing, it is accelerating, but it's not as great. And so what we can, or what we notice is, right, is that the greater the mass, the lesser the acceleration. Again, less acceleration does not mean it's not happening. It's just not as much as it would happen with less mass. Is that clear?
Yes.
Yes, Fatma, Ibrahim?
Yes.
Okay.
Yes.
Right, so keep in mind, acceleration is happening. It's not that it's not happening. It's just not as much. Right, and so we notice, okay, fine. So acceleration increases with force, but decreases with mass, right? So the greater the mass, the lower the acceleration. The greater the force, the greater the acceleration. And from this, we link into Newton's second law. So from this experiment, right, the conclusions are that force is directly proportional to acceleration, and acceleration directly proportional to force.
And the greater the mass, the lesser the acceleration.
Right? And so I'm putting a semicolon in there. The acceleration is inversely proportional to the mass. Right, let me rewrite this and to make acceleration, this appears the same thing, just switching places. Right, so acceleration is directly proportional to the force applied, and acceleration is inversely proportional to the mass of the object. Okay, so
Okay.
if we put those two together, right, what we get is, right, acceleration is something like this, directly proportional to force and inversely proportional to mass. We can flip that around, right, as we can do with all equations of proportionalities, and we can say that force is directly proportional to, right, mass and acceleration, being, right, to the, right, multiple of mass and acceleration. Basically what I did is I took that, switched it over. So it's, in the denominator here, it goes up as a numerator, right? The proportionality remains the same.
ये equal to नहीं होना चाहिए.
Sorry, what?
A is equal to F over M नहीं होना चाहिए.
I'm sorry, your voice is still not clear. You can either type it, please. Your voice is a bit garbled. So you can just type that out. I'll address your query. Okay, you're saying that shouldn't it be A equals to F over M? We are getting there. We haven't got there yet. Right now we're talking about, so this is not an equation. This is not an equation, right? This is showing the relationship between force, mass, and acceleration in terms of whether they're directly or inversely proportional, right? So acceleration
Yes.
is directly proportional to force and inversely proportional to mass. We put those two together, and so we move those around, right? We get that force is directly proportional to the multiple of mass and acceleration, right? Or if I just put a multiplication sign between, it will become clearer, right? Now, if we turn this into an equation, as you are suggesting around, right, what we'll get is force equals to K M A. All three of these are different, right? We know that F is force, M is mass, and A is acceleration, right? So what's K? Right? K is the constant of proportionality. And right, these constants of different physical quantities is something that we will come across in multiple scenarios. So this K, sorry, lowercase, that's important, will be lowercase because the uppercase K is the symbol for Kelvin, right? It's a temperature scale. So is the constant of proportionality. Now, right, there's an additional thing that we need to deal with when we are solving. So, right, we need to deal with K first and make life easier. So let's go to the definition of, right, force is measured in newtons. Right, in newtons. The symbol is N, right? And the SI unit breakup for a newton is kilogram meter, right, per second square. So S minus 2, right? Or you can write it as kilogram meter per second square. And so a 1 Newton force, right, is defined as the force which is required to move a mass of 1 kilogram or give a mass of 1 kilogram and acceleration of 1 meter per second square. So 1 Newton, right, gives a mass of 1 kilogram and acceleration of 1 meter per second square. So if you plug that into the equation, right, F equals to kma, we've got the force, which is 1, equals to k multiplied by the mass, which is 1 kilogram, multiplied by the acceleration, which is 1 meter per second square. And, simply doing the math, what you're going to get is k equals to 1. Yes?
Yes, sir.
Okay. So k equals to 1, right? And that makes life easier because if the constant of proportionality is 1, any number multiplied by 1 is the same number. So, right, whenever we're doing calculations for this, k is always 1, and so we can then rewrite the equation in a more simpler format as force equals to mass times acceleration. Okay?
Right, yes.
Okay.
Okay.
Right, and in this case, right, the force we're talking about the resultant force. Because remember we talked about yesterday, if the forces balance out, then there's no resultant force, and so there's no change in motion. Right, so if motion is being affected or velocity is being affected, then we are talking about resultant forces or unbalanced forces.
Yes.
Right, and so now that we have force equals to mass and acceleration, the multiple of mass and acceleration, obviously we can move things about depending on, right, which of these quantities needs to be the subject or is the unknown. So we can also write it as A equals to F over M. All right, Ibrahim? Is that clear, right? So this is what you were talking about. And this is what we did finally achieve.
So sir, whatever the subject we're taking as, that will be um the main whatever force we're taking, that will be the main subject, right? In the
The, f-
formula.
the force is not the main subject. The
Acceleration.
no, the subject will be the unknown basically, right? So the equation is normally written as force equals to mass times acceleration, but you can move it around, right? Just like we know that
So
density,
whatever is unknown, that will be the subject.
whatever is, yeah. So right, so density is mass upon volume, right? And you don't know the mass, so you can move it around and say mass is density times volume. Okay?
Yeah. Okay.
So that is true for all equations, right? You move them around and make the unknown try to make the unknown the subject, and right, adjust everything else accordingly, right? And remember, side change, sign change. So if there's an addition becomes a subtraction, multiplication becomes division, and vice versa. Okay.
Right.
Okay. Now also, uh, right. So I mentioned that it has to be a resultant force, and right, if the force, so if the force is acting in the direction of movement, right, it's going to cause the object to accelerate. Right, if an object is already moving, force is applied against it. That will cause the object to decelerate. Make sense?
Yes.
Right, and
But
basically,
it can, but if a force is applied against the direction of movement, like it can also change the object's direction at some
it can,
point, right?
yes, it can, right? So it can also cause a change in direction depending on how it's applied, right? Or it can cause a change in shape. And that, even if it's right, uh, that applies, right, also to if it's acting in the direction of movement as well, right? So it can cause a change in direction, it can also cause a change in shape. Okay. Now, right, that's clear. Do you want to do an example? Right, like a
What?
question based on this.
I
Okay.
can't hear you.
Would you like to do an example question based on Newton's second law?
Yeah.
Okay. So here's the question. There is a worked example in the textbook, right, that shows how a question like this can be attempted. Right, I'm not doing that one. I'm doing one that's given as practice. So what they're saying, first of all, is a force F produces constant acceleration in a straight line of 0.5 meter per second square. 0.5 meter per second square. Right? And the mass of the object is 7 kilograms. On a mass of 7 kilograms. And it's pretty simple. Calculate F. So calculate the force. And so we know F equals to A equals to 0.5 multiplied by 7, which will give you 3.5
3.5.
Newton. So that is very simple and straightforward. Okay. Another question, right, in which you need to tackle it a bit. So, right, they mentioned there is a box of mass 5 kilograms. And it is moving with constant velocity. Okay. When it is pushed by a force of 8 newtons. Then they're asking when the push is increased to 10 newtons, right? You want to calculate the resultant force. And then you want to calculate the acceleration. Now, do you guys have any idea on how to solve this?
Sir, Ibrahim gave the answer for resultant force.
Oh, he's typing?
Yeah, on the
Wow,
chat.
I didn't get a plan for that. Okay, 2 newtons. That is correct. Now, how this works, right? Remember, when you're attempting the paper, any question, anything, read it very carefully because each and every word counts and you need to pick up on the keywords, the hints, the tips that they give. So what they're saying over here is that the box of 5 kilogram has a constant velocity. Saying that it has constant velocity means it's not accelerating. Right? Which means that there is a friction force that is equal to the push, right? Which is 8 newtons. And so they're asking for the resultant, right? It's going up. And so what you're going to do is 10 minus 8, so this is the new push. This was the push that was being balanced out by the friction, right? And so you're going to subtract them. And you're going to get 2 newtons of force, right, as your value for the resultant. And because it's a resultant force, right, it's an unbalanced force. That's what we need to produce acceleration. Right? So the 8 Newton was being balanced out, therefore the velocity was constant. So that's part A, and that's the concept behind it. Part B, right? F equals to MA, and so you get A equals to F over M.
Sir, Ibrahim got the answer again.
Yeah, but I need to show the word. So you have 2 divided by 5, right, which is 0.4, right? Meter per second square.
Square. Oh, yeah.
Right now, yeah, just don't get confused. You can write it meter per second square with a slash. You can write it as the denominator, or you've done standard form, right? So you will do ms and s to the power minus 2, which is just telling you the decision between the denominator. So all 3 of these are correct. Okay, good. Now, just a right bit before we move on, and so the constant that we calculate, right? There's right. This is only true. The constant is only one. The constant is one only when you take the mass in kilogram and the acceleration in meter per second squared. Only then will you end up with a k value of 1, which is what's making your life easy. Right? If you are not following that, then the value of k will change, and then you will have to take that into, of course, that is not going to happen in your O level syllabus, right? But as far as knowing it is concerned, right? So the formula that you need to know for your O level is this, right? K is one only.
Sometimes we're given the mass in like grams, so should we have to convert it in the exam
Yes,
then?
right. So
Okay.
if you're given, right, for example, 8,600 grams, and so that's 8.6 kg. Or if it's a small mass, right? For example, it's 32 grams, right? And so,
Yes.
right, that is 0.032 kg, right? Or
Right.
3.2 into 10 to the power minus 2 kg if you want to convert that to standard form. Okay?
Okay.
So, yes. So, you will need to convert it into kilograms. You will need to have the acceleration as meter per second square, to, right? And that is, again, right? So they're not going to ask you to deal with k in your O level syllabus, but right, that's how you need to have the SI units you're dealing with as required, right? As the standard format, not standard form, standard format. Okay, that is Newton's second law. Right, you need to know it both for your O level and for your IGCSE standard syllabus. Now, before moving on to Newton's third law, right, I'll talk about extension in springs. It's a pretty basic, like simple concept. Extension in springs. And so we know that a force can change the shape or size of an object. And springs are elastic. Which means they can, sorry, not elastic, that's biology, elastic. Right, which means they can stretch. And we just did that ticker tape experiment. We used an elastic band. We know that they can stretch when a force is applied on them. The cool thing about them is that, right, how much force you apply is directly proportional to how much they stretch, or in other terms, the extension that force causes or produces. Okay?
Yes.
But not like indefinitely, right? It doesn't work in the way that you keep on stretching and you keep on applying force and it will just keep on stretching. And in case of, right, I mean, let me rephrase that. It will stretch, right? The thing about elastic materials is, right, when you remove the force, right, they go back to their original length. So the extension is removed. And so the greater the force you apply, the greater the extension, and when you remove that force, right, they go back to the original length up to a point, right, which is called the limit of proportionality. Right, the limit of proportionality is the point up till which, right, force is directly proportional to extension, and when you remove the force, the elastic material, right, whether it's a spring or an elastic band or even a metal wire, right, because metal wires have a certain elasticity, right, they will go back to their original length. If you apply a further force beyond the limit of proportionality, right, and so the spring in this case will not go back to its original length. And so it will go back, but if you started at, for example, x, every time you applied a force, it became x plus, for example, 5, and then it went back to x after you removed the force. But in this case, when you applied a greater force, right, beyond the limit of proportionality, what you had is you started off with x, you went to x plus 7, for example, right? And when you remove the force, you ended up with x plus 1. So there's some extension still left. And that means, right, the spring has actually, the elastic properties have been lost, and it's not going to work the same way again.
Right.
Any questions?
No.
No.
Now, right, as we had with, right, the second law, we had a constant of proportionality. Right, if we use the symbols F for force, right, and X for extension, so they're directly proportional. If you change that into an equation, what you get is F equals to K X, and in this case, right, K is the spring constant. So as I mentioned, right, you're going to come across a lot of constants with all being represented by the lowercase k, and you need to know, depending on what the question's about, what that constant is, right, what k represents. Now in this case, k is not going to be equal to 1. Why? Because it's a
It
spring.
will
Huh?
it will be equal to 1 when the limit of proportionality is not reached, right?
No.
No.
Right, the spring constant is a property of the spring or the elastic material. Elastic material or the spring. So the value will be different. So it will have a different value, right, depending on the type of material, on the material, right, and on the make of the spring, right, and those are factors which will affect K. So it's not something that just is, because you've got a physical, right, so if your spring is made of aluminum, or it's made of iron, it's made of some other material, how many coils there are, right, all of those
Right.
things will have an effect on K, which is the spring constant. And of course, right, as with all equations, you can move them about. So, right, in your book, it's actually, the equation is actually defined with K, right, the spring constant is defined as the force per unit extension. So in that case, right, K is actually F upon X. And so we move that about, and that's how we got F equals to AX. Right, so the spring constant is force per unit extension, and so this is the K value will be the same for any one type of string or one type of elastic material. Okay, but it will, right, so because
Right.
how much extension is produced for a certain force will depend again on the material and the type and all of those things.
Right.
Now, if you plot, right, very quickly, I'm going to make a very crude one over here. Right, if you plot a graph with extension, and remember when we're plotting graphs, right, you mention what it is on each axis along with the SI code. Right, so in this case, oh, one thing I forgot to mention. Right, the spring constant is, right, force per unit extension, and it is the force which needs to be applied to a spring to cause an extension of 1 meter. So the force required on a spring to produce an extension of 1 meter. Now, obviously, we don't have those huge springs that can actually stretch 2 meters. And so, because the smaller springs, we're dealing with millimeters. And so, if you do a calculation, and there's an example calculation in the textbook. So, right, if we have, like, if we go a bit over time, right, a few minutes, right, we'll see that we need to convert the measurements we have in millimeters into meters to actually solve the question. So before that, you have extension in millimeter, and then you've got, right, force in newtons that is being applied, and right, because these are proportional, up until the limit of proportionality, you will get a linear line. Right, the slope depends, right, but the line will be linear up until the limit of proportionality, after which it will become non-linear. Try to draw a slight curve over that, so perhaps this is better. So that is the limit of proportionality. And so you can get a graph in your question, and they'll ask you to identify the limit of proportionality. So you need to study it carefully and see up till which point is the graph linear, and then from which point does it start to become non-linear. An easy way of doing that is just plus, if it's printed on paper, obviously you place a ruler along this part of the line, and you see, right, till which point is it going straight, and as soon as the line starts to deviate from your ruler, right, that is the limit of proportionality. And then they'll ask you what force was applied or what was the extension, right, produced up till the limit of proportionality, so whatever the question is. Okay.
Yes.
Now, a quick question, and for this one, I'm just going to give you the worked example in the text. So there's a spring that is stretched by 10 millimeters. By a weight of 2 meters. And we know weight is also a force. 2 newtons. 2.0 newtons to be exact. Right? 2.2. And they're asking you to calculate, first of all, the spring constant. Right? So they're asking you to calculate K. Now for K, we need, right, we have the force in newtons. This is in millimeters. So we need to convert that. So 10 millimeters, right, will be divide that by 1,000 and get right 0.01 meters. Then you do the math. So K equals to F over X equals to 2 upon 0.01, which will give you 200 Newton per meter. That is right. So this is the SI unit for spring constant. How did we get that? Right, you got Newton over meter. Simple. Right, the extension is in meters. The force in newtons, Newton per meter.
Right.
Then the second part of the question is, right, what is the weight of an object that will cause an extension of 80 millimeters? Right, so weight for extension of 80 millimeters. And so now we have the spring constant, so that's where it comes into play, right? It's useful. We know, right, first of all, 80 millimeters equals to 0.08 meters. Right, so that's one thing we have. Then, right, weight is a force, so we move around. F equals to kx, which means you have right 0.08. Sorry. Oh, sorry, not the force. Wait, why am I confusing myself? Oh, okay, sorry. So yes, 0.08 is the extension and 200 Newton per meter is the constant, right? And so 200 multiplied by 0.08 is going to
16.
give you 16 newtons. And how did we end up with newtons? If you just look at the units, right, you've got 0.08 meters multiplied by 200 Newton per meter. That cancels out. These two multiply, and you're only left with the Newton number.
Right.
Right? These are the kind of questions that you will get. And so we've covered the spring constant as well. We've done the second law, right? And we did that experiment. So these three things were covered. Next class, right? Next week, talk about Newton's third law. And yesterday I mentioned that it's not part of the IGCSE syllabus, right? It's not part of the syllabus. I mentioned it's not even in the book, but it is in the book. It's given as a going further topic, right? So it's not part of the syllabus. You don't need to know it, but it is there in the book, right? So when I cover it in next class, right, you can, if you're interested, you can read it in textbook as well. But you don't, for the IGCSE, you don't need to know. You will not be asked questions based on Newton's third law.
Okay.
Okay. So all good, all clear. Any questions?
No.
No.
All right. So, all right. I'll see you guys next class then, inshallah.
Yes. Okay. Allah Hafiz.
Allah Hafiz.
What did you say?